Now we are getting into the molecular structure and bonding theory. So there are two different things here, okay? So one is the 3D shape of molecules, and the other one is a little bit of a different kind of a bonding theory, okay? So you know about the Lewis theory of bonding. We're going to learn about one more, okay, in this chapter. So we'll start with the 3D shapes first. So we know that, we exist in a three-dimensional world. We are 3D people ourselves. And so molecules have definitely a 3D shape. Okay, so as soon as you have a triatomic or a polyatomic molecule, it's going to have 3 dimensions. Linear molecules like, the diatomics, they have a 3D structure as well because the atoms themselves have volumes, right? So they are also three-dimensional, but they don't have any bond angles. So when we talk about shapes, we have to talk about the angles also in there, okay? And so I'm not saying that the diatomics don't have a 3D structure. They do in a different way, okay? So what this does for us, okay, in a 3D shape of a molecule is that we can explain some of the properties that molecules have. So for example, why water is a liquid, but carbon dioxide is a gas, even though both of them are triatomics, right? So you can see there's oxygen, there's, three atoms here, 3 atoms here, but they behave very differently at room temperature. So why is that? And so this is something that we can study using the three-dimensional structure, okay, of molecules. We can also try to predict some of the properties and how these molecules will behave with each other in a 3D environment once we know the structure of the molecule. A lot of the biological interactions that we have in our own body, the enzymes, the proteins that we have in our body, they are all very, very much space oriented. Okay, so here are some examples that you can look at if you want to. And sickle cell anemia is a really, you know, very good example of this in the sense that, just one amino acid in, a whole bunch of amino acids. And this is not a whole bunch as in like 10. A whole bunch is like 200 and something amino acids, and in which one is replaced, okay, and it just completely changes the whole 3D structure that now hemoglobin is not able to bind to oxygen. So it tells you how critical the 3D structures are for us, okay, in our lives. So how are we going to do this? Okay, we are going to learn this through the VSEPR theory, and the VSEPR theory is the valence shell electron pair repulsion theory. And what this is in a nutshell is that if you have electrons that are next to each other, they are going to repel each other as much as possible. So negative repels negative, right? Opposites attract, and then the similar things will repel each other. So that's kind of what's happening. So in a central atom, you will have electrons, and those electrons, whether they're bonding or non-bonding, they will repel each other as much as possible, okay? They will try to get away from each other as far as they can. Now, you can't break a bond, right? Because that would change the molecule. So that's not what's happening, but they're going to try and stay away from each other as much as possible, okay? To make sure that, the repulsion is maximum. So in order to predict the structure, or the 3D structure of a molecule, you need to have the correct Lewis structure. And I cannot emphasize this enough, okay? So I was talking about this even before when we were talking about Lewis structures, is that if you don't have the Lewis structure correct, everything else is going to be wrong, okay, about it. So Lewis structure is really your key to understanding this chapter also and being able to do everything right. So make sure your Lewis structure is correct. Once you have the Lewis structure, then you look at what is called the electron domain geometry, and from there you get the molecular geometry. So I'm just going to call this electron geometry, okay? So I don't have to worry about domain, but really this is what you're looking at, because remember, you're looking at the electron repulsion. So you need to know where the electrons are. Once you know where the electrons are, then you can figure out the molecular geometry. So it's a step-by-step process. So first of all, I want you to understand electron groups, okay? Because electrons are the ones that are going to be repelling each other. So you need to understand electron groups. Most important thing for us, the Lewis structure, is that you show all the electrons in there, okay? So When you write a structure like this, for example, BeH2, and these bubbles that I have drawn over here, these are just to show you that this is one group of electron, and then this is one group of electron. Now, the group of electron that we are looking at is a group, okay, that is bonded together, whether it is a single bond, double bond, or a triple bond. It doesn't matter. Yeah, this is a triple bond. Okay, the bubbles kind of, on it, but it's a triple bond here. It doesn't matter, okay? It could be a lone pair of electron also, okay? So for example, over here, there is a lone pair. That is also a group of electrons, okay? So the group of electrons can be bonding, non-bonding, and then if you have a double bond, that is also one group. If you have a single bond, that is also one group, okay? So it's really important for you to understand how many groups of electrons we are talking about, okay? So in this structure, if you have the Lewis structure correct, you can see that there are two groups, okay? And where are those two groups? We are looking at the central atom. Whenever you're trying to do the molecular geometry of any molecule, the most important thing is the central atom. The terminal atoms matter in the sense that you have a terminal atom versus a lone pair of electron. Okay, so if you have a terminal atom, that's important. If you don't have it, that is also important because then you have a lone pair, or you don't have a lone pair. Okay, either of those cases. So it's an important thing. Okay, so know where your electrons are on the central atom. So here's carbon dioxide. And here are your groups of electrons that you're looking at. So the double bond is one group. Now note that I have not circled any of these lone pair of electrons on oxygen because they do not determine the shape of the molecule. The central atom does. If oxygen was in the middle, then yes, it would. Okay, but oxygen is not in the middle, so it's a terminal atom. And so because of that, oxygen doesn't affect the shape of the molecule. Okay, it's just that it's terminal atom. So the electrons on there don't matter. Electrons on carbon matter. And here we have two groups. Here also on the carbon, you have two groups. Again, the lone pair of electrons on nitrogen does not matter. It should be there, okay, but it's not going to affect your central atom grouping, okay, for the electron. So I hope you understand what I'm trying to show here. So again, boron with three groups, and then here, even though you have a double bond, that's one group, and so on. Okay, that's how we determine the electron groups. Okay, so this is the first step, okay, is to draw the Lewis structure and identify your electron groups. I'm going to teach you how to use Axe formulas to determine these electron groups and shapes. Okay, and if you learn the Axe formula, trust me, you're going to be on the right path to learning this thing very well. Okay, because the Axe formula gives you a lot of information about a molecule. What is the Axe formula? A is the central atom, X is the terminal atom, and E is the lone pair of electrons. So in the case of sulfur dioxide here, this is A, this is X, and then this is E. Here, in this case, with the carbon double bond oxygen and hydrogen, there is no E. Okay, so this would be AX3, for example. This is also AX3, for example. There is no E in here because there are no lone pair of electrons. Okay, so the Axe formulas are written just like any kind of a formula, okay, chemical formula that we write. So we'll talk about that more also, okay, as we go on. So here it is, okay, a little bit more about the Axe formula. As I said, we'll talk about this. So here's the Axe formula definitions. And so this is just to explain to you a little bit in case you missed anything as to how we write the Axe formula. So AX2 indicates that there are two terminal atoms, X, and on the central atom is still A, okay? A is always going to be your central atom. If you have more than one central atom, you're going to have more than one Axe formula. It's just that, okay? So just because you have a large molecule doesn't mean you just have the one Axe formula. That's not true, okay? So the more central atoms you have, the more Axe formulas you have. So A is just a central atom. And remember what we have for now. We have the kind of bonding that we have learned. We have learned that there is the octet rule. What is octet rule? Octet rule means 8 electrons. What does 8 electrons means? 4 pairs of electrons. That is AX4, okay? Meaning that you have 4 bonds out of the central atom. That's the maximum we have learned. Then also you all have the expanded shell. Okay, yeah, then so we're going to talk about that also. Okay, so just remember, keep those Lewis structures in mind as you're doing your Ax formulas also. Okay, so here with AX2E, what this means is that you have a central atom, you have two terminal atoms, and then you have one lone pair of electron. Just like any formula, if you don't have any lone pair of electrons, you don't write the E. So here we didn't write E because there is no lone pair of electron. But if there was one, you would write the E. You don't have to write E1. Okay, so just leave it as E. Ax formula is very easy, okay? Once you kind of understand it, then you cannot live without them, okay? They're also very easy and they're really very informative, okay? So what we are going to get from the Ax formulas is the electronic geometry. What is electronic geometry again? Electron domains, okay? How many electrons do we have on the central atom? Because the electrons are being indicated by the terminal atoms and also the lone pair of electrons. Okay, so we are accounting for all the electrons right here. So that gives us the electron geometry. Okay, the electronic geometry is not necessarily the shape of the molecule because the lone pair of electron is not an atom. It's just electrons. They are still repelling other electrons, but there is no atom there. Okay, so the shape of the molecule then is determined by the atoms that you have. The lone pair will affect the shape also because it's still going to repel. All right, so you can see that these two things are equally important, okay, for us. So as we go on, I'm going to try and explain to you how they are important and how they are related also, okay, to each other. Because with electronic geometry, you can get a lot of information, and then the molecular geometry gives you a different kind of information. So let's look at AX2 first, okay? And AX2 is a central atom with two groups, okay, or two terminal atoms, excuse me. Those two terminal atoms can be connected anyhow. It doesn't matter, okay? And these are the series of molecules I gave before also, right? So here, two groups, single bonds, two groups, double bonds, two groups, single group. It doesn't matter, okay, what kind of bonds you have, so long there are just two atoms in there, okay? So here, two atoms and two atoms. Lone pair doesn't matter, okay? So now they will be as far away from each other as possible because that is the valence shell electron pair repulsion VACPR theory. They're going to be far away from each other as possible. So the farthest they can get from each other is 180 degrees. Okay, so they can't get any farther away from each other because after that they'll start getting together on the other side, right? So they are as far away as possible. So the central atom here, which is kind of a purplish pink, I don't know what color this is, but anyhow, whatever this color is, that's the central atom. The blue ones are the terminal atoms. That's the AX2. So now the electronic geometry is linear because this is a straight molecule, just like that. Okay, the molecular geometry is also linear. Okay, straight molecule. Bond angle 180. Okay, and the angle is really going to be the important thing for us because how far apart are these two terminal atoms from each other? That's the key thing, okay, because that's determining the shape of the molecule, right? How far away these atoms are from each other. These are the characteristics that we are going to keep looking at for any Ax formula, what the electronic geometry is, what the molecular geometry is, and what's the bond angle. Okay, those three things are going to be important. Now, these two can be the same depending on if there is any lone pair of electrons or not. Okay, so that depends. So we'll see as we go on. This was AX2, where you had two terminal atoms. Now, if you had three terminal atoms, now things can be a little bit different, okay? Because in a three terminal atom system, what does it mean? Okay, it means that here you have literally three atoms attached to boron. So H, H, H. So if you have one electron group, three and two and three electron groups, right here is pretty visible, okay? This structure is also like that in the sense that you have these two atoms and then you have the the double bonded oxygen. Okay, so you have an atom. Even though it's a double bond, it doesn't matter. It is still a group. Okay, over here. So these two are kind of similar structures in the sense that you have three atoms. This structure is a little bit different because now you have two atoms and then you have a lone pair of electrons. Okay, over here. So this is sulfur dioxide. Okay, and sulfur, remember, has 6 electrons. So 4 of them are bonded here and then 2 are left behind. Okay, and remember, sulfur is the one that can have an expanded shell. So it can have more than 2 bonds. Okay, oxygen is supposed to have only 2 bonds, but sulfur can have more. So sulfur here is bonding with oxygen. And between sulfur and oxygen, what do you put in the middle? Whatever is below, that's what you put in the middle. Okay, so sulfur and oxygen form a double bond and you have a lone pair of electron left over. Now structures 1 and 2 are different because this is not exactly AX3. This is actually going to be AX3E. So E meaning lone pair of electron. Okay, that's kind of what it is. This is what the schematic would look like. Okay, where you have the 3 groups. Okay, that's kind of what it is. And you might think, oh my God, this just looks like this. It does. Okay, but this one bond, you kind of have to imagine this as a lone pair of electrons for structure number 2. Okay. All right, now let's look at the characteristics of AX3. So AX3, the electronic geometry is what we call trigonal planar. Planar means that it is in one plane, like flat molecule. Okay, so it's a flat molecule. If you lay it down on a table, it will just lie flat. Okay, that's trigonal planar. The molecular geometry is also trigonal planar because this is AX3, and so the molecular geometry is the same as well. The bond angle here, the farthest they can get from each other is 120. Remember, a circle is 360 divided by 3, and that's going to be 120. So that's the characteristics for AX3. What about AX2E? Now for AX2E, the electronic geometry is still trigonal planar. Why is it trigonal planar? It is trigonal planar because you have 3 electron groups, 2 plus 1. So that is trigonal planar electron geometry because you have 3 electron groups, but you don't have 3 terminal atoms. You only have 2. So the molecular geometry, or what we call the shape of the molecule, is bent. Okay, because there's nothing on the top here or on the side here. It doesn't matter, whichever one. So if you pretend that this is not there, not pretend, it is not there because there's a lone pair of electron here, then you only have these 2 left, and that looks like a bent shape. But the bond angle is still that of AX3. So the bond angle is still 120. Why? Because the electronic geometry is trigonal planar. Okay, the bond angle is related to electronic geometry. The shape of the molecule is not related to electronic geometry. In some ways it is, okay, but the bond angle is more related to electronic geometry. Molecular geometry depends literally on how many atoms there are, okay, on there. So that's going to matter a lot, okay, for us. So, and let me not confuse you, okay, I mean, molecular geometry is dependent on electronic geometry also because you need to know how many electron groups there are, okay. But what I'm trying to say is that the bond angle is derived from electron geometry, which is the number of electron groups you have on the central atom. Now let's look at the 4 electron group, okay, AX4. So in AX4, you have 4 atoms coming out, or you have the 4 electron groups. So these are the black lines, right, that you see here. So those are the 4 electron groups. There are 3 variations of this. The 3 variations are where you have 4 atoms, another one where you have 3 atoms and then a lone pair, and then you have 2 atoms and 2 lone pairs. So the one with the 4 atoms is AX4, the one with the 3 atoms and a lone pair, AX3E, and then the one with the 2 atoms, 2 lone pair, AX2E2. Okay, that's what this is. So these are the 3 variations possible. Now, if you see the way I have drawn all of these structures for you, they are all kind of like a tripod. So here is an antenna, and here is the tripod. So imagine these legs are going to the back, this is coming to the front, okay, of you. So if you were to draw it out yourself, this is what it would look like, okay. Generally, when we draw something with 4 atoms, we tend to draw it like this, okay, when we're drawing Lewis structures, and that's fine. So the example here would be that, you know, this one, CH4. So when you were learning Lewis structures, you would draw CH4 like this, and that's perfectly fine, okay. Now that you're learning a little bit more, now you know the shapes of molecule, now that you're learning about the electron groups, now you're going to see, oh, but that's really not what it looks like. It actually looks like this, okay? It's going to have those 3 legs and an antenna on it. So it's a different kind of a shape. This would be like a square shape, right? But that's not really what CH4 is. By the time these electron groups are repelling each other, this is what the shape would look like, okay, or this is what it would look like, okay, and I've made a complete mess of everything here, but anyhow, that's what it would look like. So one has to be careful. So a CH4 or an AX4 kind of geometry is called tetrahedral, okay, and a tetrahedral meaning the one coming up and then 3 prongs going down. The bond angle of this one is not 90 or anything. It is actually 109. Whether you're looking at this bond, this bond, this bond, it doesn't matter. Whichever bond you're looking at, they're all going to be equal bonds. And again, I'm going to show you a video of that on another video I'll make of it, okay, not on this one. So you can see that video where I show you the molecule, and you will see that they're all exactly the same bond angle. It might seem that, oh, how can that be? But it is true. At least these two look alike, right? And this might seem to you that, oh, this looks like a trigonal planar where this is 120, but it's not. Don't forget this is still there. Okay, so either you can pretend this is going to the back or you can pretend this is coming to the front, depending on your visualization. But otherwise, this angle is 109. Okay, all right. So AX4, which is tetrahedral, has an electronic geometry of tetrahedral. The molecular geometry is also tetrahedral because it's AX4. The bond angle is 109. This is for the first molecule here. For the second one, you still have the 4 electron groups, but now you have a lone pair of electrons. So this is AX3E. So the electron geometry is still tetrahedral because there are 4 electron groups. But the shape now, the molecular geometry is trigonal pyramidal. So just remove this. If you remove this top part, what do you have? Just a pyramid. Okay, in there. So this is trigonal pyramidal. You have to write pyramidal because previously with the AX3, we learned trigonal planar. Okay, so this is not planar, this is pyramidal. Don't just write trigonal and just leave it like that. Don't do that. Okay, the bond angle is related to electron geometry. So that's tetrahedral. So this is still 109. Okay. And you can see this for all of them, okay, because this is coming from the groups of 4 electron groups, the bond angles are all the same, okay. So here with AX2E2, which is the last molecule, which is water, and water and oxygen is in the middle, and you have 2 lone pairs on oxygen. So this one now is AX2E2. The electron geometry is still tetrahedral because there are 4 electron groups. The geometry is now bent, okay. And bent, you still have a bond angle of 109, okay? Now, if you go back to AX3, you will see we had a bent shape there also. And in that one, the bent shape had a different angle. And you can go back and check that, all right? But that was an AX3 geometry. Now we have an AX2E2 geometry. Now our bent is different, okay? I think that one was AX2E. So that was different, and now this is different. The shape is still bent, but the bond angle is different. Why is it different? Because the electron geometry is different. So you can see the importance of electron geometry in helping you to remember bond angles, okay? So AX formula is very, very helpful, okay? Let's go on more to see AX5 now. I've given AX5 and AX6 on the same one because we're not going to do too much detail, okay? I try to focus a lot more on our octet molecules, okay? But these two are the expanded shells. Remember, if you have AX5, What does AX5 means? That on the central atom you have 5 electron groups attached. What is 5 electron group? 5 times 2, because each line is 2 electrons, whether it's bonded electrons or non-bonding. So 5 times 2 is 10, so that's 10 electrons, and 6 times 2 is 12 electrons. Okay, so you have AX5, AX6 geometry. This is what the molecules would look like, okay, in here. So let me explain what I've done here. I've tried to show you 2 different drawings, so either whichever one helps you, because it's hard to draw 3D on a 2D paper, right? So that's kind of a challenge. But anyhow, so here I've connected everything on one plane with lines. So you can see that this is in one plane. The one going up and down are in one plane. Okay, so the blue ones are going in one plane, and then the purple ones or pink ones, whatever, purple I think. Anyway, they're going in one plane. There are 3 bond angles here: 180, 120, and then between the blue and the purple, that's a 90-degree bond angle. Okay, so there are 3 different bond angles in this one. Now, if you are asking, okay, what about the other variations like AX4E? Yes, there are other variations, but we are not going to cover that. I need you to know the AX5, and the AX5 electron geometry is called trigonal bipyramidal. Okay, bipyramidal because there is 2 groups going up and down. So there is a pyramid on the top and there is a pyramid at the bottom. So that's bi, that's 2. Okay, bipyramidal. The other groups, the other compounds with the AX5 electron geometry will have the same electronic geometry, but they'll have a different shape. They will still have the same bond angles, right? So I hope at least that much that we are being consistent in, okay? And we've learned that. If you have something of an AX6, okay, so AX6 geometry means you have 6 electron pairs, okay, and those 6 electron pairs now are looking like this. Again, the lines here, the lines joining the 4 atoms, they're on the same plane. So here the same color, they're on the same plane, the blue are in the same plane, okay. Here you only have 2 bond angles. This one literally is a square actually, okay, if you think about this. These ones just follow my laser and get dizzy. But anyhow, so these ones, this is literally in a square. And so this angle over here is 90. The angle between the blue one and the purple one is also 90. But the one between the blue and the blue is 180. Okay, so there are only 2 bond angles over here. This is an octahedral geometry. Octahedral meaning 8 faces. So there are 4 faces on the top, 4 faces at the bottom, like a pyramid. Okay, so that's what it looks like. Again, there are variations of AX6. Okay, we're going to look at that also. But those variations, again, can get complicated because which atom to remove, right? So if you're writing AX5E, well, AX5E is okay, but which is the E, which is the lone pair? Is it this? Is it this? Is it which one is it? So that can get complicated sometimes for us. Okay, and that's why I try to focus in here only on the octet rules. Okay, these ones you just need to know the main electron geometry, and for all of the work you have your notes. Okay, so you can go ahead and look through, and I have no problem with that. So here is all the geometries all on one page, and I've tried to draw this. I know it's very crude drawing, but it's all there so you can see how things are in one plane, okay, over here. So the blue here are in one plane, here also these 2 are in one plane. Now, when you get to the tetrahedral, things start getting out of plane now. Out of plane, literally you have a 3D structure, okay, which means things are coming out of the paper, things are going behind the paper when you draw it. You cannot draw that on a paper and give it justice, okay. Then trigonal bipyramidal, you already saw that, okay, and again I'll show you all of these molecules in a separate video, okay, in a 3D form. So here your imagination has to work, and again these blue ones are all on the same plane and the red ones are in the same plane, okay, that's how it works. So here are all the number of electron groups, and that gives you the AX formula. Then you have the shape, okay, on here. Now this shape that we are writing for all of these, this is more coming from the electronic geometry. That's what it says here, okay. So this is not the molecular geometry, this is electronic geometry. I've given you examples and I've given you what it looks like in a ball and stick model. Okay, this is what everything is. So again, here is some more. I've given you a little bit more detail. So again, this is just so that you get used to seeing these molecules and you understand what's going on in a different way. So if this suits you better, then this is fine. Okay, so in this one, there's a little bit more detail as in AX2. AX2, this is the only one possible, okay, because you only have two atoms. If you remove one atom, then you have only a diatomic structure, okay? AX3, now you have two variations, right? AX3 and then AX2E. Here in this structure, you can actually see this bubble, the balloon here. That balloon shows that this is where the lone pair of electron is. Okay, that's all it is. And so the shape is going to be bent. The bond angle has not changed. All right. Here is for AX4. Tetrahedral is the electronic geometry. Bond angle is all the same. The shapes are going to be different because in the case of AX3E, you have one lone pair of electron. AX2E, you have two lone pairs of electrons. So that's kind of what it looks like, okay, eventually. So again, whatever suits you, okay, whatever kind of diagram you like, you do that, but you have to learn these shapes, okay, of molecules. Here's the AX5 and AX6, okay, so these are the various shapes that you can have, but the electronic geometry is the same, okay, it's a 5 electron group and 6 electron group. And then here you can see how we are taking out one by one atom and then putting in the lone pair of electrons, and these are the shapes that you get. Now if you don't remember these shapes, it's okay. All right, this is the one that I need you to know. But once you have the AX4E, then this one is called the seesaw. Actually, this one is a little bit different name, but the fun name is seesaw. And then here is a T shape, and then it gets linear as soon as you have three lone pair of electrons and you only have two atoms. It will be linear. So that's actually quite simple. Okay, it's not that complicated. Initially it is, because initially you don't know which one to remove and put the lone pair of electron on. Okay, so similarly here also with AX6, where do you remove the atom? Which atom do you remove in order to get the lone pair of electrons? Okay, and so it can be a little tough, so I don't put you in that challenge, not yet. Eventually sometime we will, but not right now. Okay, here is another table of all the examples here for you. Okay, so here I want you to see that I have made this table according to electron groups. Okay, so 2 electron groups, 3 electron groups, 4 electron groups. As soon as you start having more electron groups, you start having more variations, right? So 4 electron groups, you have 3 variations: AX4, AX3, EX2, E2. With 5, you will have more. 6, you will have more, okay, in there. And you can see the electronic geometry is consistent here for the AX4, and the electronic geometry is consistent for the 5 electron group and then 6 electron group, but shapes can be different. Okay, I've given you examples over here. You can write more on your own if you want to, but this table kind of gives you the whole picture of everything that we have done so far. Here is another picture. Again, whichever one you like. You might think that I'm repeating myself too much, but for me, the more examples I give you, the better I feel. Okay, and you can also see whichever one you like better, you use that. If you like the table, use the table. If you like pictorials, you use pictorials. So here is a solved problem. Use the VSEPR model to predict the geometries of the following molecule, ASF3 and then PH4 plus. For all of these things, the most important thing for you is going to be drawing the Lewis structure. If you don't draw the Lewis structure properly, nothing is going to work. Okay, so make sure you're good in your Lewis structure. So ASF3, this is the structure for it. AS is in the middle, arsenic is in the middle, fluorine is all around. Arsenic is in group number 5, so after 3 bonds it has 1 lone pair left over. So you can see this is going to be AX3E, right? That's what it's going to be. So that's what the shape will be, AX3E, AX3E. The electronic geometry is tetrahedral, and the actual shape is going to be trigonal pyramidal then. Okay, this is the Lewis structure. This is the actual shape, okay, of the molecule. pH 4 plus. Now it doesn't matter if this is an ion, okay? This is a neutral molecule, this is an ion. It doesn't matter. Ions also have shapes, okay? And so you just have to write the proper Lewis structure. So here is the Lewis structure for pH 4 plus. So you can clearly see that it's going to be a tetrahedral, okay? Because it is AX4 electronic geometry. Okay, here's another one, ICl3, ICl4 minus. Again, drawing the structure is the most important thing. So here is the Lewis structure. So here is I, okay, I know it's kind of melding in with the lines, but here is I in the middle. Iodine, it's a halogen, and if halogen is in the middle, it can have more bonds. But if it is terminal, it can have only one bond, okay? So if Cl was in the middle, it would have more bonds. And I terminal would have only one, okay? So anyhow, this is the structure. 3 chlorine. So 3 chlorine will have, the chlorines will have one bond, okay? It can have 2 bonds with iodine though, okay? Because chlorine, starting from chlorine, you can have more bonds on chlorine because chlorine can have expanded shell. Iodine has 3 bonds also because it can have an expanded shell. So chlorine, bromine, iodine, they can all have expanded shells. Okay, so depending on what the chlorine is bonded to, it can have more bonds. So be careful with that. Okay, so here is the structure for ICl3. We don't have to worry about drawing double bonds or anything like that because everything is paired up, right? All the electrons seem to be paired up. If there was any single electron, then I would say, okay, let's look again, okay? But everything is paired up. So all is good. So there are 5 electron groups and there are 3 bonding, 2 lone pairs, so which means it is AX2E2. And then the electronic geometry is trigonal bipyramidal. And the shape is the T shape. Now remember, for AX5, 5 electron, 6 electron geometry, you can check your notes, okay, if you want to. Okay, ICl4, I can see that we're going to have 4 chlorines on all around iodine. So again, it just shows you, right? Here is also iodine in the middle and you've added another atom, so that's what we have now. And we've added an electron also, okay, on this one. So that added electron also goes on the iodine in the middle. So this is what the structure would look like. You can probably see what this is, AX4E2, right? 6 electron groups, okay, that's what we have now. So AX2E2, and the electronic geometry is going to be octahedral and the geometry shape is square planar. And you can look, okay, if you want to. Okay, so now if you have more than one central atom, what do? It doesn't matter, just be patient, okay, with it. So if you have CH3OH, you draw the structure. How do you draw the structure? Hydrogen can never be in the middle, okay, you know that already. Carbon and oxygen then will be in the middle. So connect them first. Once you connect them, then you can see that there are 3 hydrogens on this carbon. So you put the hydrogens here, there is a hydrogen for this oxygen, and connect that there. At this point, usually I try to help you and guide you if there is more than one central atom. I give it to you in an order, so that way you know how many atoms are connected to the central atom, okay? So don't make it too complicated. So here we can see this central atom here, C, and then we have 4 electron groups. Oxygen also has 4 electron groups, but 2 of them are lone pair of electrons, okay, in there. So the first one, which is carbon, AX4, no lone pair, so it's a tetrahedral. Oxygen, AX2E2, and 2 lone pairs there, so that one is going to be a bent shape, okay, in there. So it's very simple like that. And if you wanted to go ahead and draw the shape, that's kind of what it would look like, okay? So you have the tetrahedral here, and then this is kind of the bent shape, okay, that we have for oxygen. So that's what it looks like. So now we're going to take the shapes of the molecules and take it to the next level, and the next level is dipole moment. Okay, so we have learned about polarity of molecule before, and the polarity of the molecule is determined by electronegativity. Okay, Electronegativity is the pull of electrons towards itself in a bond by an atom. And electronegativity, if you remember, increases as you go to the right, decreases as you go down a periodic table. So in the case of HCl, Cl is more electronegative, and it has then a partial negative charge, and hydrogen then ends up getting a partial positive charge. So this bond is polar, the molecule also is polar. Okay, now I'm going to introduce one more term here for you, which is called dipole moment. Dipole moment is a measure of how much a molecule can move in an electric field. It's the negative charges that move in electric field. Okay, remember that electrons conduct electricity. So which means you need to have partial positives or negatives, in there. Sorry, negatives, not partial positives. You need to have the partial negatives in there. So which means we need something that is electronegative, which is fine. That's okay that you have partial negatives, but you also need to have a shape that will help you determine if you're going to have dipole moment or not. Okay, because some molecules may not have a dipole moment even though they have polar bonds. Okay. All right, so first of all, dipole moment is given by this symbol. It's called mu, okay, just like micro, if you remember from back when, okay? So dipole moment is represented by mu. If we say there is no dipole moment, we just say mu is equal to 0, okay? That's it. But if there is a dipole moment, we have to show it, okay? And we'll do that, of course, right now. So how do you determine dipole moment? Number one, write the Lewis structure. Nothing is happening without the Lewis structure. So you have to write the correct Lewis structure. All the electrons in there. Determine the shape of the molecule. Determine the electronegativity, okay, of each of the atoms that are in there. The shape of the molecule is now not only just the electron geometry, but literally the shape also. Is it bent? Okay, that kind of a thing, or is it tetrahedral? Electronegativity from the periodic table, and then you should actually show that electronegativity. So for example, you can write directly on the bond and say, okay, well, here this bond is polar. Okay, so that way you can clearly see that chlorine is pulling more electrons. So if you don't want to write the delta minus, that's okay. That red arrow is also going to show you that chlorine is more electronegative. Okay, now after that, you're going to see if the molecule is symmetrical or not, because if the molecule is symmetrical, then it will nullify the charge separation. Okay, so what does that mean? Okay, it kind of means something like a tug of war. All right, so if you have a central atom and then you have two atoms on either side trying to pull electrons from it, if they're equal in strength, the central atom is not moving anywhere. All right, so that's kind of what we're talking about here. So I call it a tug of war, kind of like the electronegativity. Okay, and then after that you determine if a molecule is polar or not. If you do all of these things step by step, you will not go wrong. Okay, so just take it step by step. Okay, so let's go ahead and do that. And here we are, dipole moment of triatomics. So diatomics, not a problem, right? Diatomic, the HCl, we saw that there back there also, not an issue. Triatomics and the more complicated molecules are going to have issues. Okay, so let's go ahead and try this one out. So this one here is, let's see, the first one is a water molecule, and the water molecule is AX2E2. And the shape of the molecule is bent. Okay, so you can see that over here. So what I have shown to you here is that first of all the shape is bent. Okay, then this oxygen here, this is pulling electrons towards itself. Those are the red arrows, so they are pulling electrons towards itself. Okay, oxygen atom. So then because the molecule is bent, now this oxygen can pull electrons on one side. Okay, so it's kind of like a tow truck trying to pull two things at an angle. If it was going in the opposite direction, it's not going to work. All right, so it's pulling in the same direction, and so it is going to have a dipole moment. How do you show that? You show it by this arrow. Okay, and this arrow we've used before also. This is an arrow with a cross here that shows dipole moment. Okay, The next atom that we have here is BeCl2, which has an AX2 geometry. So Be is in the middle and Cl is on either side. And so in this case, no, this is linear. And then the molecular geometry is also linear. So if both of them are linear, then in that case, the bond angle here is 180, right? If it's 180, then they're completely opposite each other. And so chlorine here is pulling electrons towards itself, but Be cannot move anywhere because both of the chlorines are pulling equally, okay, on either side. Now, if I were to change that, okay, so for example, if I had something like this, BeBrF, okay, which looks kind of weird, but this is really what I'm trying to say, that if I were to switch out the atoms from 2 chlorines to 1 fluorine and 1 Br, well, now things are a little bit different. So even though this is linear, fluorine is way more electronegative than bromine is. So poor bromine is trying to pull, but it's not having that much effect because fluorine is more electronegative, and so you will have a dipole moment. BeCl2 did not have that because both the chlorines are the same. So that is the effect of symmetry in the molecule. This is a symmetric molecule, all right, and therefore it can have a dipole moment. Now H2O, just to kind of put a little icing on it and finish it off, this looks very symmetrical, okay? It is kind of symmetrical molecule, but it is not symmetrical because the pull is not symmetrical. Oxygen is way more electronegative than hydrogen is, okay? And there is a bond angle of 109. Because of that, you end up having a dipole moment. All right, now for some more, okay, over here. So the first one, which is ammonia, this is AX3, and it's not just AX3, it's actually AX3E. So apparently I have some errors going on here. So AX3E, so electronic geometry is tetrahedral, the molecular geometry is trigonal planar, okay, and it's not trigonal planar. What's going on here? It's trigonal pyramidal. Okay, there, fixed it. So AX3E, and then electronic geometry is tetrahedral, molecular geometry is trigonal pyramidal. So if it is trigonal pyramidal, then everything is at an angle. And what is that angle? That angle is 109. Okay, so which means that when nitrogen, being more electronegative, pulls towards itself, it is pulling electrons towards itself. So you are going to have a dipole moment, okay, in that case. So then let's look at another molecule, which is the sulfate. Now when you draw the sulfate molecule, look at this. Sulfur is in the middle and oxygen's all around. This is an AX4 geometry. The AX4 geometry in this case is all very symmetrical, okay? And because this is so symmetrical, the sulfur is not going anywhere. So bond angle is 109, and now sulfur is not moving anywhere. So the dipole moment is 0, okay, for sulfate. So that's kind of what, how you work out the dipole moment, okay? And I'm sorry about all these errors. I'll fix that in the writing, but here we have it, at least in the video, okay? All right. So here are some more dipole moment problems. So just go through these. You can see how I worked everything out. So I've explained it in the previous, problems also. You draw the Lewis structure, you write the electron geometry, you write the shape of the molecule, you determine the symmetric nature of a molecule, and then you then decide from there, okay, whether something is going to have a dipole moment or not. Okay, so dipole moment, yes, this one is also going to have dipole moment. And that's it, I think. So we are done for this portion.